chapter 5 in the book deals with basic relay logic. And then we'll look at what we call, anybody know what logic is? Except not logical mind. In electricity and electronics, we have what we call logic operations. We have ands, ors, nands, nors, nots. And then we got some what we call comparing instructions. So we call these things, and relay, giving us the ability to make decisions like that is what's led to automation, right? You understand that? Where we can have relays make decisions. I've shown y'all relays, right? Everybody okay with a relay? That's an electrically controlled switch. Well, the way we use this, and this is in the textbook, but we're going to revise this a little bit. This guy don't act like he's ever been through relay logic, even though the book is pretty good. But we call it relay logic. So we'll look at use symbols to represent different types of input and output devices. Create a relay logic diagram. I don't know why my display is kind of purple. Place comments on relay logic devices using the standard rules. This is what we're going to use. We're going to see the standard rules, not the rules that's in the book, the standard rules. Create relay logic for a process of industry control. So relay is sometimes called a line diagram or a ladder diagram. So that's fine. So PLCs, what is the L in PLC? What is PLCs, what does that stand for? Programmable logic. Yeah, programmable logic control. So relays, we literally wire the logic up with wires and relays and push buttons and stuff like that. Programmable logic controllers, we do the logic with a program. Now it doesn't do away with relays, and it doesn't do away with inputs. We'll go back to the line here in a little bit. From here on out, relay logic described as ladder logic diagram. So that's what we're going to do. First step is creating a program for a PLC. Now this is not true anymore. Used to, there was when I first got into programming, we had the mainframe we had here was an IBM 360. And it was one of those computers that sometimes you see on old music that had all the flashing lights and everything on it. It had a tape drive on it, so originally we saved our programs on tapes. And then they had two big old disk drives. There was 300 megabyte disk drives, and now we don't even, megabytes to us is way down here, so we're up into terabytes now on our mass storage devices. But the way they entered programs into the computer is the programmers would write the programs, and what they would do is they would start off with what we call a flow chart, where you had all these symbols that you'd use to create the flow of the program. And if it wouldn't flow in a flow chart, it wouldn't work on the computer. Then after that, they would take their flow chart and they would develop their program on a computer. And then what they would do is they would send that to a key punch operator. And the key punch operator would punch these big old 132 column cards. And then they would run it through a card reader. They'd take it to the computer operator. So most programmers never even saw the computers they were writing their programs for. And they would take it, these punch cards, they had holes all in it, and they'd feed it into a card reader, and then they would run that and bring the program into the computer. And then they would try to compile it over. If it didn't get any errors, they would see if it worked. If it got errors, they would send those errors back to the programmer, and the programmer would try to correct those syntax. So originally what we did when we got into PLCs came up through relay logic. So the electricians that wired these circuits, they understood relay logic. So normally when they did a PLC program, that's what they would do. They would start off with the relay logic, and if it didn't work with relay logic, it wouldn't work. It wouldn't work in a PLC. We very seldom do that anymore because PLCs have been around for a pretty good while. So most of the time it's a hit and miss thing. So we just start doing programming, and we'll see that in this class. But we're going to have to do both of them. So every once in a while, they'll give you the PLC program and they'll ask for the relay logic program that would represent your PLC program just to get you in the flow of it. So we'll call these relay logic. First step is creating a program for a PLC. Is to create a PLC relay logic, not necessarily, but we need to know the difference because PLCs has not done away with relay logic. It's just enhanced it a lot. Show the symbols. We do diagrams. When we draw diagrams, we use symbols. We don't draw the devices. We pictures of the devices. We use symbols. After relay logic diagram is drawn, it's converted to a PHC ladder logic diagram, often called a ladder diagram, but this is not true. Not always. Okay. And what you'll find out real fast is we're going to teach you a terminology, but usually a lot of times when you get into a company, they've got their own terminology. Of course, that's what you'll have to adapt and say, well, that's what that means. Use the program, ladder diagrams, use program PLCs. Programs defines operations to be performed by the PLC. So the PLC does the logic. So we read inputs. These are going to be all your push buttons and all your sensors and everything. We run it through a logic, a program that you're going to learn how to write some this semester, and then it's going to generate outputs. And the outputs are going to turn on lights, they're going to turn on solenoids, or they're going to energize relays. Voltage between two rails, labeled L1 and L2. Sometimes they're not. Sometimes they're derivatives of this. The problem we have is a lot of times the power that feeds the circuit. Oops. I'll stick this anyway. So we have two rails, they call it power rails, and we draw a vertical like this. And sometimes we call them L1 and L2. We do that a lot for discussion. But what happens is that usually companies have multiple voltage levels. It's just like at your house. You have two voltage levels at your house. Anybody know what those are? Nobody in here knows the two voltage levels at your house? Now we have 120 and 240. We have 240. What do we use the 240 for? Why do we need 240? Over in Europe, it's all one. It's 240 over in Europe. That's all they have. Over here, we have two. So we got a little better sense than they do over there. Yeah, so what people don't understand is that all conductors have an R. They have a resistance. Currently, we don't understand something that has no R. And what happens, if y'all had DC yet, we can calculate, so anytime we push electrical current through a resistance, it creates a voltage drop. Electricians call it, and that would be like any impeding, so they come there and they check their blood pressure all the time. Normally when people have heart attacks, it's because their veins have become clogged in the blood. We have opposition in the blood vessels now, and it impedes or reduces the flow. So the problem is we can calculate the amount of push that we lose to a resistor. It's called Ohm's law, and it's V is equal to I times R. So you can look up charts that tells you the amount of resistance a conductor has. In fact, if you're familiar with the National Electrical Code, the National Electrical Code tells electricians how to safely or correctly install all this wiring that runs through your house. What size wire to use, what it's all set up for, right? So anytime I push current through a wire, it drops the voltage. So this is why when you look at the cables going up to the battery on your car, they're really, really big, right? You understand? Because that's one of the things that determines the resistance a wire has is how big it is, what material it is, and of course temperature. And this is why, for one reason, this is why a lot of times your car won't crank. It's strictly because you got a little bad connection in there. You added, so if I put 1 ohm of resistance into my wire, and it takes 60 amps to start my car, that means that thing would try to drop 60 volts. Well, you don't have 60 volts to work with. So what happens? Your car don't crank, right? You understand? Because you're getting all your loss inside the wire. Well, what we're trying to sell. So what type of bill do you pay does you or your parents pay every month for the work you get out of your electricity? Or you pay a power bill. So in electricity or power is equal to force times speed or force times distance. If y'all learned that back in a physics class in school. So our force is volts, and then our speed is current. So this is our main power formula right here. This is not anything you have to know right now, but by George, you're going to learn this as you move through your electronic field. You can probably ask Corey over here. So what we've got is the power company's trying to send you power. They're not trying to give you volts. They're not trying to give you current. You're paying for work, right? The amount of work you get from it. Well, if we rearrange this formula, we found out that I is equal to P over V. So I'm trying to send you power. The higher I can make that voltage, the less current's required to provide you that power. So this is why we have these substations and everything all out through our electrical grid. And what they do is they step that voltage up real high for transmission, which causes the current to go down, right? Does that make sense? Which means they have less line loss. So odds are this company is not going to have a safe voltage. So what we usually have up here is we have 3 phase, and they're called L1, L2, L3. Well, what problem? I'm calling my L1 and L2 over here. This might be 660 volts. This is not 660 volts. So I'll show y'all the U.S. Steel prints. They call theirs PL1 and PL2. So it's going to be some variation for that. So normally what we do is we'll come over here and we'll bring this through a transformer. And we'll step it down. So what advantage does low voltage have? So all your high wattage devices run off of 240. So these now we can run smaller gauge wire, right? You understand that? To run those devices. All the other devices in your house run off 120. So what advantage does 120 have over 240? It's safer for you to be around. So 120 is a lot safer. So where's all the plugs and everything for 240? They're behind the appliance down at the baseboard, right? You understand? So you'd have to do what to get to your dryer? You have to pull your dryer out, or if you got an electric stove, you'd have to pull your stove out to get to that. If you got an electric water heater, it's going to be hardwired. It's going to have a disconnect. If you got if you got an HVAC system outside, it's going to be hardwired. So those things are not easy to do. In 120, you got all these plugs around your house, right? You understand? So it takes more current to produce the same amount of power, but it's a lot safer. Now the problem we have so 120 volts has been around for years and years and years and years and years and years. So the advantage AC, alternating current, has over direct current is we can easily step it up for transmission and start stepping it down for safety using transformers. But what they did is they came out with a code. It's called the National Fire Protection Association, 30E. This is a safety standard. That's fire rich. This is a standard that basically tries to keep you from getting electrocuted. And what they've done is they've set up a voltage level of 50 volts. They consider anything over 50 volts to be illegal. So for years and years and years, the control voltage was 120 volts because it was readily available, right? We had a bunch of transformers. But now they've dropped it down to a lot. So we're not going to be dealing with, we're going to be dealing with 24 volts DC up here. So that's safe, right? You understand that. But if I call this L1 and L2, that would be very confused with this L1 and L2 over here. So usually they give it a different name, but they'll put another letter in front of it or something like that. So it's not, your control circuit is not always going to be called L1 and L2, but it's going to be similar to that. And then what we do, we come up here, we build circuits between L1 and L2, which we'll call it that, right? But it might not always be that, right? In fact, on the PLC, they don't even call them anything. It's up to you what you want to call them. So I'd start right here. And then I would come over here and I would put a symbol. So this is a symbol for a push button, a momentary contact push button. And then I would come over here and let's redo this. These are supposed to be dots like that. So this would be a normally closed. So that means it's closed, and when you touch it, it does what? It opens. And then we'll come over here and put one of these. So this would be a normally open momentary contact push button. And now I come over and put this. And this is a symbol for a relay coil. I understand that now. Everybody okay? Are we okay? All right. So a relay coil, we come up here, we put current through it, it generates a magnetic field, and it causes contacts to either open or close. Then what we'll do is we'll give this thing a name. I'm going to put it inside because it'll see it. I'm going to call this CR. And then I'm going to come over here and put this. And any contact that's controlled by that relay, we give it the same name. Right now, I'll just call this stop. I'll call this start. But that's a circuit started. Then I come down here and I might do what? I might put another circuit. So these circuits that's drawn between L1 and L2, these are referred to as rungs. And you can see why it's given the name a ladder diagram, because it basically looks kind of like a what? Like a ladder. So we have two power rails. They're vertical. They're always vertical. And then we draw our individual circuits between L1 and L2, or between CL1 and CL2, whatever it's called at your plant that you go to work with. And each one of these are called a rung. Now we got to come over here and we got to follow basic rules. So that's a symbol for a light. We'll call it a red light. So if you don't know the symbols, then the diagrams don't mean anything at all to you. So we need to learn some symbols, and we'll use some of these same symbols inside our PLC program. So we'll look at symbols. So we're going to go ahead and look at basic. We'll look at some of the basic symbols right now. So they're not always called L1 or L2, but there's usually some derivative like that. Usually L1 and L2 is in there somewhere. Each individual circuit drawn in a relay logic diagram is called a rung. A relay logic diagram will have one or more rungs, right? Are we okay? Question? So this would be a relay. So a relay comes in, we have a push button, we push the button, generates the current flow through the coil creates a magnetic field, opens and closes contact. So the top is what we call a normally closed contact. We don't have anything wired up to it right now. And the bottom would be normally open. So normally closed means if this button's not pressed, the top contact's going to be closed. The bottom contact will be open. I press the button, and the bottom contact closes. Now, if I was to draw the diagram for this, if it lets me, it'd be a real simple circuit. I would come over here, I'd draw my two rails. I come over here and put a normally open momentary contact. I'd come over here and I'd put a relay, we'll call it CR. Then I would come down here and draw another circuit. I'll give this contact the same name. And then I would come down here, and then I'd draw the symbol for the light. And that would be the ladder logic diagram for that circuit. Now this looks pretty easy, but when these things get more and more complex, it's easier for me to look at that and figure out how it works than actually see the actual physical layout of the circuit itself. So this is a symbol for a limit switch. I think I showed you all the limit switch over there the day when we were back to the lines right there. This little mechanically operated switch, the thing strikes. So I come over here, and they don't have this drawn real good. They got those real close. The space should be wider. So what's going to happen on this one? I press the button. I momentarily press the button. This is going to bring in CR. CR is going to come up here and close this contact. Now we have a secondary path through here. Okay. So it seals itself in. Now I can let go of the push button, right? You understand? Because we got a secondary path. It's going to close this contact down here, and this solenoid is going to energize. I'll show the little solenoid, right? And then, of course, when it comes up here and it's this limit switch, the limit switch opens. This is the normally closed limit switch. It calls CR to de-energize. This contact will open, and then everything will go back to its normal state. Are we okay? So this is the ladder diagram. You see how complicated it is. There's a lot more information that they're not actually showing. So what they're doing is they're given, so these things consist of a rung. So this right here would be a rung. This light, by the way, goes up back over to L2. I don't know why it didn't draw it the other way. So that's a rung. Now you notice on the left-hand side, we have numbers over here. And we're not numbering the rungs, we're numbering what we call the lines. So a rung consists of one or more lines. So anything that runs horizontal like this is considered a line. So this rung has two lines. So in motor controls, what we do, our relay logic, we don't number rungs, we number lines. And then what they do over here, which we can't see, so this is better. This is actually a print we got from U.S. Steel that runs number 4 galvanizing. You can actually see the line numbers. In fact, this is actually page 137. Can you imagine this print? This is 137 pages so far. So this right here is line 1. This right here is line 2. This right here is line 3, 4, 5. Then when I come over here, by the way, these are wire numbers. This is what we use to wire, but we're not going to deal with that in this class. Is over here, they give this relay a name. 5B, if y'all can't see it, it's 5B1DE, .dB. And then what they do is they come over here and they put these numbers over here. Can y'all see that? It's 137-2. We don't need the 137 because that means it's on this page. Now what this is doing, or 02, it's telling us where the contacts that's being controlled by this relay, where they're at. So if I come over here and look at line 2, and I start following it over, there's that contact right there. So what we do in motor controls is we give lines numbers. We don't give what? We don't give rungs numbers. We give line numbers. And this is one thing that's really big and different in PLC. And then what we do is we give a relay coil a name, and then over here we put the line number where the contacts are located that thing controls. This has got a normally closed contact. It's underlined in line 57, but I don't have line 57 on my drawing, but I would know to go look for it, right? It says this relay's got a contact in line 7. So here's line 7, and what is that? Yeah, there it is right there. So instead of me trying to draw lines like I did back over here, showing you these contacts, we give the line a number, right? So this is wrong over here. This shouldn't be like this. This should be 1. That should be what? 2. And that right there should be 3. And then we'd come over here. So every horizontal line gets a number. So what the book does, they're numbering rungs and not lines, right? You understand? So this is where the book is wrong. And then over here I would have 2, and I have 2, and then I have comma 3. So this came out of the book. And you need to know that because you're going to get into motor control. So the book, like I said, this guy, motor control or in relay logic, we number lines. And every line line up, they get the same number. So if I was to come over here and put a light in parallel with this one, since it lines up, it does not get a number. It gets the same number. So draftsmen really make sure they line these things up as many as they possibly can, so that way they don't have to use a bunch of line numbers. So these are line numbers. Every horizontal line gets a number. These are what we call cross-reference numbers, which shows you the location of the contacts that a relay coil has. As you can see, the problem is they cut this off over here. Yeah, just that one, they cut this off over here. Here, you can't see it, but you can definitely see the line number. 12 rules are accepted as a standard. So y'all go ahead and take a break. 10 minutes guy that wrote the book. He did a real good job. But so this is for relay logic. So if you take motor control, you'll get this again. Rule 1, control devices such as switches, push buttons, relay contacts, and sensor contacts must be placed between L1 and the rung button. Everybody understand that? Rule 2, output devices such as relay coils, lights, small motors, and solenoids must be placed between the control devices and L2. One and only one output device can be placed on each rung line. Now this is true in PLCs also. So the guy in the book really gets confused right here. A rung is an electrical circuit that runs between L1 and L2 that consists of one or more lines. Magnetic motor starter overload contacts are the only thing allowed between the motor starter coil and L2. All other rung loads must be connected directly to L2. Motor starters. So the problem we have with motors is that when you start them, they pull about 6 to 8 times what they do when they run. But so you have to fuse them for getting them started, right? You understand? So if the motor don't start, then the fuses are not going to blow because they're designed to let the motor start, right? You understand? So what we do is we have a sensor inside the motor control, inside the circuit. So this is three phase. These would be the contacts to run the motor. And then we'll come over here and these are symbols for overload sensors. So what these are looking for is they're looking for overcurrent over a certain amount of time. And then my motor would be right here. So these are overload sensors. And we can see these on the line. And then what we do in our control circuit, if I was to come over here and redraw that control circuit that allows me to start stop and seal in. Or over here, I might call this a motor, a M1, a motor starter. And then right here, we'd put a set of contacts. That's the overloads. And this right here would be L2. So these are the overloads, the actual overloads themselves. Overload switch, I guess you call it. So if the motor don't start, it opens this contact right here, and there's no way in the world you can get current flow to the motor starter, so the motor will drop out. So that's technically the only thing that's allowed between L1 and L2 is if the relay is what we call a magnetic motor starter. It's a motor starter. And the only thing that's allowed between L1 and L2 would be the overload contacts. That's being controlled by these sensors that are inside that's part of the motor starter. And they've got a couple of these even on the Amatro line. They don't have any on the Festo line, but they do now. So all other loads connect directly to L2. The only thing that's allowed between the rung load and L2 is if it's what we call a magnetic motor starter. Rule 3, control devices can be connected in series parallel or series parallel. The connection of control devices does not determine if the circuit is series parallel or series parallel. What determines that is the way we connect our loads. Multiple rung output devices cannot be connected in series. However, multiple output devices can be connected in parallel in a different line. Within a rung, only one output device can be connected in a rung line. The rule is one or more output on a rung, but only one output per line. There are no multi-load series circuits or series parallel circuits allowed in relay logic or PLC. There are some PLC programming applications that let you get by with this, but if it works here and don't work on another PLC, that's going to screw you up, right? So what we're doing is we're giving you the rules to follow for every PLC that you'll program. Rule 5, control devices such as switches, relays, and sensors with a single contact can only be used once in the relay logic diagram. And that would be back over here. So I come over here. So this little thing right here. Okay. So I come over here and how many normally open contacts does it have? One. Well, then I can't come over here now. I can't come over here now and I'll just stick it anywhere. So I can't come over here now and draw this circuit. I can't come over here and do this. Okay, so I'm just going to put a push button. I'm going to come over here and put my relay coil. And we'll call it CR. Well, I can't come down here and say CR, so there's not one normally closed contact, and make it control a light bulb. And then I can't come down here and use another normally open and call it CR and let it control like a relay. Because I've only got one normally open contact, right? You understand that? So you can't use the same contact multiple times inside a circuit. Now, if it's got 15 open contacts, that's fine. It's just that you can't do what? You can't use the same contact multiple times within the same circuit. This is a big difference in PLCs, by the way. So that rule makes sense. Can't use the same contact. Can only use the same contact one time, right? Rule 6, each relay, rung, output load must be assigned a name. So notice mine, I'm calling them CR, I'm calling it M, but over on the US Steel prints, they gave them big names, right? You understand, like 6 characters. It's up to where you work, but you should give them a name. And then what we do is we put the contacts that's controlled, we give them the same name. And that's the way you So each relay rung output must be assigned a name. The name should be written above each rung load. The name is usually an abbreviated version of the function of the load within the control circuit. So what they did on the US Steel prints, they was real nice on there, is they gave you what each one of them stands for. So we were looking at 5P1PT. Over here I see 5P1PT. Right here. This is number 5 dynamic braking contract. I don't know what that is. It tells me what that actually stands for. So normally you want to give the relay a name on basically what it does inside the circuit, right? So that way it makes more sense to you. They use these abbreviations, but if you use stuff like that, then you need to probably provide a list that tells you what they actually stand for. Okay. What was that? What rule was that on? Okay. The name is usually abbreviated. Rule 7, each contact controlled by a relay must be given the same name as the relay that controls the contact. We saw that, right? Rule 8, an output device can only be represented once in the program. So I can't put CR up here and then use it down here again, right? Does that make sense? All control devices and output devices symbols must be placed horizontally. So we either, in schematics, guys, we don't have anything that looks like that. All our lines are either vertical or horizontal. That's even true on schematics when you get into electronics. Signals in a relay logic diagram must flow from L1 to L2. Signal flow must never flow backwards. So we don't force it to flow back to L1. Diagrams should be numbered, commented correctly. Unlike PLC logic diagrams, horizontal lines are numbered and not rung. Line numbers are placed to the left of L1 adjacent to the line. Any line that aligns horizontally with another line gets the same number. Comments can be written to the left or the right of the rung, so US Steel wrote them over to the right. The location of each relay contact controlled by a coil is identified by writing the line number of the contact's location to the right of L2. And adjacent to the coil, that symbol that controls the contact. Multiple contact line numbers are separated by commas. A normally closed contact location is underlined. These numbers are referred to as numerical cross-reference numbers. So I showed you those on that US Steel print, right? So this is the US Steel print. So these are numerical cross-reference numbers. Or that control, right beside the coil. And this gives us the line numbers where they're located. So I know right now, this 5B3M has a contact in line 7. Go down to line 7, and then there it is right there. Luckily, those are one on top of each other. So that's the rules for relay logic. Now what we're going to do is we're going to look at the rules for PLC logic. So if you take motor control, you'll get that same handout. Creating a relay logic diagram for industrial controls, clearly define the control problem, draw a schematic diagram of the system setup, discuss the problem, review and follow the 12 relay logic diagram rules, and draw the relay logic. These are the revised rules. These are the rules that we'll follow some of these rules do not apply to RS Logic. So we teach so RS Logic 500 is the older programming applications for PLC. But the problem is there's thousands and thousands of these PLCs that are programmed by RS Logic 500 out there. So if you get out to a system that's been there for more than 3 or 4 years, then odds are it's going to program with RS Logic 500. The new programming application is called RS Logic 5000, which they renamed to Studio 5000, even though they're basically the same. These rules kind of vary on those guys, but what we're going to learn is that if I learn these rules, it applies to every PLC that programs in ladder logic that I've ever ran into. Rule 1. We don't have to worry about this. This is going to give us an error that will not clear until corrected. Input instructions must be placed between L1 to the left rail and the rung loads on the right vertical rail. It should be noted that any instruction that the programming application places on the L1 side is considered an input instruction. So if I try to put a contact between my load and L2, it's going to give us an error. Rule 2, error that will not clear until corrected. Output instructions are placed between the control devices and L2. Nothing is allowed between the rung's output instructions and L2. We don't have motor starters inside a PLC program. That means we don't have overload contacts in a PLC program. We'll have to figure out how we would wire those to an input, but we don't have those. So in PLCs, nothing is allowed between the load and L2. All L3, this is automatic. You don't have to worry about this. All input instructions must be placed horizontally. You don't have to worry about that. That's automatic. But that's one of the rules that the writer of your book put in there. Rule 4, a rung output instruction must not be placed in series with another output instruction. Multiple rung output instructions can only be replaced in parallel in another line. One output instruction per line, one or more output instruction per rung. And this is where the guy, he says in his book, one goes for a rung, he says, rungs and lines. Y'all understand the difference between rungs and lines now, right? This rule does not apply to 5,000, but it's still a good rule to follow. You know, RS Logic 5,000 is it. Rule 5, error that will not clear until corrected. Program flow execution is from L1 toward L2. We can't make it run it back toward L1. Rule 6, rung numbers are automatically placed on the left side of each rung's first line. Rule 7, user defined. This is not automatic. Each input and output instruction's address is entered above each instruction symbol. So in computers, we're going to deal with addresses. So we're going to have to learn how to address our inputs and our outputs. This location is predefined by the ladder logic programming application. A block input instruction, which we'll get into when we get into counters and instructions. Block input and output instructions address is entered in a predefined location inside the device's symbol. All newer PLC programming applications require what we call symbols or tags. And we'll get into that. This is one problem I have with RS Logic 500. We'll show you. Optional for RS Logic 500, but this is going to be required in this class. Each input and output instruction should be assigned a symbol. Or if they've changed the name, now they call these tags. So if you get into RS Logic 500 or the TIA portal, they're going to talk a lot about tags. in new PLC programming applications, these are called tags and are required. Once a symbol name has been assigned to the name can be used to repeat an assigned address within the program by name instead of address. So this is kind of like your cell phone. So, you know, somebody gives you their number, what do you put it in? You put it in your contacts and you give it a name. So now, from now on, you don't have to even know the number. You can call them by what? By name. It's just like the internet. The internet uses something called IP address. But we're using something called DNS, domain naming system, that allows us to get to these websites by name instead of knowing their IP address. And that would be hard because we're going to an IPv6, which is a 148 bits. Those addresses are like this. Rule 8, user defined, not automatic. Optional comments should be added to each instruction symbol. So the more information you put on a run, the better it's going to be from you 3 years from now when you come back and you try to figure out what in the world you were trying to do. So you just say, you know, this run does this. So that's very easy. So a comment and a symbol or a tag is not the same. Rule 9, user defined, not automatic. This is going to be required for this course. Optional input symbols should be given a name that relates to the instruction's function in the control circuit. Use of a symbol tag allows the logical address to be addressed by name instead of number. Rule 10. So what we're going to do is we're going to assign all our instructions a name. We're going to assign them an address, and then we're going to assign that address a name. And then once I assign it a name, I can do what? I can use the name instead of having to remember all these addresses. Rule 10. Input and output relay contact instructions can be used multiple times within the PLC program. Output instruction addresses should only be used once. So we can use contacts. I can have one push button, and we can use that same contact hundreds of times inside the program. And if you press that one contact, they're all going to close. So that's a big difference in programming. Rule to create relay logic. This is your book. Input instructions are placed between L1 and the run output. L2 output instructions are placed between the run's input and L2. I don't even know if we're going to go through all of these. This is what they're talking about, flow backwards. So right now, we're running this way. And this contact mode, I take the path back and go off. I take L1, that's not good. So this way, this contact mode, it's got multiple paths. That's not so good. So y'all okay? Y'all got any questions on that? Okay, we need one more thing to go through, and then we'll try to let y'all play around with the PLC a little bit today. Well, I can actually, yeah, I have mine picked up. So this is our first introduction to programming.